Hi, everyone. Hey, let's talk about solutions. Not solutions to your problems, well, maybe chemistry problems, but aqueous solutions and other types of solutions. Okay, so this is a little bit different than other videos. We're just going to go through some definitions, some terms that we need to know when we talk about solutions. Okay, so let's start with the basics. What is a solution? Well, as you saw in the previous slide with the test tubes and the Erlenmeyer flasks, solution is simply a mixture of two or more substances. Usually one is liquid and oftentimes water. Water is essential to life. We're dealing with water all the time on planet Earth. So usually our solutions are aqueous, water-based. But the chemist actually has a broader definition of solution. It's simply mixing two or more things. That's a solution. So you got typical things like seawater. Sure, that's a solution. That has water and salt and a bunch of other stuff. Alcoholic beverages, there's alcohol in there with water and other things that give it its flavor. But gasoline, shouldn't be any water in there. Gas that you pump in the car, it's actually not one compound, it's a mixture of a whole bunch of different hydrocarbons, molecules containing carbon and hydrogen. But turns out brass is technically a solution. Okay, so there's nothing liquid there. It's simply a mixture of copper and zinc. Oh, there's a picture of brass down here. Brass is copper and tin. Okay, it's a mixture of two metals. So technically it's a solution. And you can have gases dissolved in liquids. If you have carbonated beverages, soda pop, yeah, that's carbon dioxide, a gas dissolved in water. That's a solution, even though one thing is a gas, the other is a liquid. So solutions, simply two things or more being mixed together. We can go one step farther. We can define one component of a solution to be the solvent, the other thing to be the solute. So the component of the mixture in greatest quantity is labeled the solvent. So your aqueous solutions, coffee, tea, sodium hydroxide in the lab, water is the major component. So we call water the solvent, right? If you, and then all the other compounds then will be labeled as solutes, the things being dissolved in the solvent, right? So back here, salt is a solute, water is a solvent, and the two together, solute plus solvent equals a solution. What about for brass? I know it's a solid. How is that a solution? Well, broad definition of solution is a mixture of two or more things. So I had to go look it up. What's the composition? So brass is actually copper and zinc. I wonder if I said that correctly earlier in the video. Anyways, mixture of two or more things makes brass a solution, which means then we can label one a solvent, the other one the solute. Well, here, this type of brass has 94 to 96% copper and about 5% zinc. Well, in that case, copper is a solvent, the thing in major supply, and zinc is going to be the solute. Simple as that. Solute and solvent, right? Scientists love putting new names on every new idea. Here's another idea. We got something called heterogeneous, something else called homogeneous. What's the difference? Well, many of our solutions are uniform throughout. Usually that means you can see through them, not always. Like these are colored solutions, but I'm hoping you can see that this part of the solution, this part, every part, it's the same consistency. Nothing's different. It's very uniform. Or in other words, whatever compounds are dissolved in here are totally dissolved, distributed throughout the solution equally. It doesn't matter about the color. The color's the same everywhere you look. Maybe that's how you think about it, just very uniform. And uniform mixtures are called homogeneous. Heterogeneous mixtures are not uniform. So typical solutions that are heterogeneous are milk and Italian salad dressing. So you zoom in on Italian dressing, you got this top layer. I don't know if you can see it. It's olive oil that's separating out. And then you got little spices in here, maybe some pepper and stuff. Okay, and then down here is a lot more of the spices and herbs, whatever's being thrown into the Italian seasoning. There's also vinegar in here. Vinegar and oil don't mix. You shake them up, it becomes cloudy. Those are all signs of heterogeneity. Heterogeneous means it's a mixture that's not uniform. You can see that the top part is very different from the bottom part. You can see little specks in here. So if you zoom in on a speck of solid, a kernel of pepper, that's different from the oil part or the vinegar part. Okay, so you go to different parts of the solution and it's not the same, not uniform, therefore it's heterogeneous. Milk, you have to view it under a microscope. If you view it under the microscope, you actually see little fat globules, little bubbles, little oil droplets, and then you got the rest of the milk, the aqueous part. It's a mixture of fats and water and proteins. Okay, and if you zoom under the microscope, then you can actually see that, yeah, there's differences. Right here, this is oily, and then right here, that's more liquid water. So there are differences, it's heterogeneous. What else we got? Okay, solutions are where one thing dissolves in another. So the term for that is miscible. So if two things are miscible, it means they can dissolve in one another. So alcohol, ethanol, the alcohol of beer and wine, yeah, that readily mixes with water. So if you put a little bit of water into pure alcohol, they dissolve, they are miscible. You can take a little bit of alcohol and put it in the water, and they dissolve, they are miscible. Oil and water don't mix, so the term for that is immiscible. They don't mix. Miscible sounds like mixable. That's how I remember it. Miscible means, yeah, they mix together uniformly and they completely dissolve in each other. And if they don't, like oil and water, you can shake them up and it gets cloudy for a second, but then they'll separate back in the oil and water. They're not mixable. They are in fact immiscible. Yeah. We also use the little slogan, what do we call this? Little memory aid, like dissolves like. So we said that compounds that had the same or similar intermolecular forces, they usually dissolve in each other. So the chemical formula for alcohol that's found in beer and wine is ethanol, this molecule. And then, you know, the chemical formula of water, but more importantly, there's an OH group that can hydrogen bond. And there's an OH group that also can hydrogen bond. So both alcohol and water are capable of hydrogen bonding, one of the strongest intermolecular forces. And since they are alike, they both can hydrogen bond, we predict that they should dissolve in each other. We predict that they are miscible. There you go. Okay, and then as scientists, we like to throw in the numbers. It's not enough for us to say either yes, dissolve, or no, they don't. How much dissolves? Let's quantify it. Okay, so the new term is called solubility. And so if there's a question in the homework that says, what is the solubility of salt in water? You're like, that's a weird way of asking if salt is soluble. And it's like, well, no, actually, what's a number? How many grams of salt can dissolve in how many milliliters, in this case, of water? What is the solubility? And it turns out at room temperature, at 20 degrees or so, you can get 35.7 grams of table salt to completely dissolve in 100 mils of water. That's the max. That's the maximum solubility. If you try and put in 40 grams in 100 mils, there'll be some undissolved salt left over. 35.7 grams dissolves in that 100 milliliters and then no more. That's the maximum, unless you change the temperature. We'll talk about that near the end of this video. If you reach that maximum, we then call that solution saturated. It's completely filled with the molecules. 35.7 grams will completely saturate 100 milliliters of water with salt. That's the maximum. And if you prepare that solution, go get 100 milliliters of water, throw in 35.7 grams of salt, that will produce a saturated solution. Okay. Growing up, I was more familiar with the term saturating, meaning, you know, if you're washing the floor, washing cupboards, whatever you have to clean up with a wet rag. If my mom said, make sure it's saturated, that means I had to soak it in the pail of water and lift it out so it's just totally dripping. And usually mom didn't say to use a saturated rag because it would splatter everywhere. So you kind of wring it out so it has some water, not the maximum. So if the rag has some water, not the maximum, we would say it's unsaturated. You can do the same thing in chemistry. Let's say you put in 2 grams of salt into 100 mils of water. It's not saturated in salt, it's unsaturated in salt. It all works, right? Anyways, be familiar with the term. If it's saturated, it means we've maxed out on the amount of solute, the amount of things we can dissolve in the solution. Okay, electrolytes. This one's actually a big deal. For those of you who exercise or you're runners, you might drink Gatorade or a sports drink of some type to replenish your electrolytes. Turns out as we sweat, we don't sweat out pure water. No, we sweat out some water that contains salts. Salts, they're found in the bloodstream. And so you start losing these salts. You lose too many, you might cramp up, get muscle spasms. So you have to replenish those salts. And another word for salts are electrolytes. Electrolyte has 2 definitions. You should be familiar with both. The direct definition, meaning, well, why is there electro in the name of this word, electrolyte? It's because literally you can conduct electricity with these solutions. We'll jump down here to the bottom of this slide. We got a light bulb here that's being lit, and we're connected to a circuit. And what's happening is we got one wire going into electrode into an aqueous solution, that's water. And there are some salts dissolved in here that allow the electricity to flow through the liquid. It conducts electricity very well because you can see how bright that light bulb is getting. So that's a good test for strong electrolytes, molecules that tend to separate in ions. Let's see, I'm jumping again. Let's go back and finish our definitions. Electrolytes, that's any material like table salt that conducts electricity when it's dissolved in water. So an electrolyte would be sodium chloride. On the sports drinks, you'll probably see potassium chloride. Potassium ions are required in the body. It's a good electrolyte. Electrolyte also means those substances that actually form ions when they dissolve in water, because that's actually how water conducts electricity, is through the motion of these ions. Okay, there are 3 types of electrolytes: strong, weak, and non-electrolytes. And all just depends on how many ions are being produced. The strong electrolytes mean every single molecule separates in ions. So if you have crystals of table salt, dump them in the water, you can see those little crystals shrink away. Well, what's happening is the little ions, sodium ions, chloride ions, are separating and freely swimming about in the liquid, moving about in the liquid, and all of them dissolve. Oh, excuse me, a weak electrolyte is something that does not completely separate in ions. So if you take a Tums antacid, drop it into a cup of water before you drink it or eat it, if you have an upset stomach, too much acid, you want to do a neutralization reaction. Turns out that calcium hydroxide is not very water soluble. Most of it remains as a solid, even though it soaks in water. But a little bit dissolves so that you get some calcium cations and some hydroxide anions. But not every bit of that antacid will dissolve. Most of it remains a solid, even though it's submerged in water. It's a weak electrolyte. Not all the molecules separate in ions. And then there's some that just don't separate at all because they're not ionic. So here we got blood sugar, glucose, and there's a bunch of carbons, hydrogens, oxygens. They're all nonmetals. Nonmetals bond to nonmetals by covalent bonds. So this molecule doesn't break down to form ions at all, but sugar does dissolve in water. That's a good thing. How are we going to get this blood sugar through the blood if it's not dissolved in the aqueous solution that blood is, right? So if you had some sugar crystals put in water, they too shrink away, but individual sugar molecules are dissolving and kind of moving about in the liquid. but you hook it up to a light bulb and the light bulb does not turn on because there's no ions in solution. It is not an electrolyte. It's a non-electrolyte. Cool. Oh, that's a nice picture. I should have shown that earlier. Scrolled up a little bit more. Yeah, so over here, I like this picture about the weak electrolyte. As you can see, there's some molecules that are completely intact. The molecules I circled have not yet separated in ions, and maybe they won't. A few of them, however, have. And so because there are at least some ions, it's an electrolyte. It's a weak one because not all the molecules have separated. And this weak electrolyte will make the light bulb glow a little bit because some current can flow. It does allow some electricity to flow in the circuit. Ooh, okay. That's all done there. Let's work on a couple more ideas. Solubility and temperature. Okay, there's two trends that you need to be aware of. There's the trend where if you take solids and you heat them up in water, more tends to dissolve. So if you want to make rock candy, sugar candy, you can take there's just table sugar in a pot of water, and some will dissolve at room temperature, but you can get more to dissolve if you heat up the water. The hotter it gets, the more that will dissolve. Increase the temperature, more dissolves. It also explains why we make coffee and tea with hot water and usually not cold water. The hot water can dissolve more of the molecules that make up the dried up tea leaves and the roasted ground up coffee bean. Take a dried up, ground up roasted coffee bean, that's a mixture of solids in there. Pour hot water on it, and a lot of those solids will dissolve. There's a lot of caffeine in there that's a solid. It dissolves in the hot water. And you actually just extract more of those molecules, dissolve more of those molecules, and make, well, in this case from the picture, a nice strong cup of tea. If you don't like your tea so strong, well, you can use cold water and less of the tea molecules, the molecules that make up tea, I should say, fewer of those molecules will dissolve in cold water, and it'll be a weaker cup of tea. It may actually taste differently because some molecules have different solubilities. Some are more soluble than others. Okay, that's the pattern for solids. Heat up the water, more dissolves. It's the opposite for gases. You know that if you ever taken a warm can of soda pop and open it up and it just squirts all over the place? Yeah, so if you have a cold can of soda, more carbon dioxide, the fizz, will stay dissolved. But if the can warms up, more carbon dioxide comes out because it's not as soluble. It's less soluble. Most gases are less soluble as you increase the temperature. Yeah, so warm soda pop doesn't taste good because the gas has come out. It's less soluble. Cool. Henry's law. Okay, so we saw up here that if you change the temperature, you change the solubility. Gases, you want to lower the temperature to make them more soluble. What about pressure? I like this one. This one I can visualize. If you want to get more gas to dissolve, squeeze it in. Just force it to go in. So you got this container on the left, and all the little spheres represent gas molecules. Let's say it's carbon dioxide, and we're trying to make some soda pop here. So we just put in some carbon dioxide gas up above the sugar solution that's going to be our soda pop, and some of the carbon dioxide will dissolve in the water. And it makes it a little bit fizzy, but you can squeeze on the gas, and actually that will push more of the carbon dioxide molecules into the liquid to help it dissolve. So right here, the middle picture is where you just start to squeeze on it. As you increase the pressure, the molecules move faster, and now more can go into the liquid. And at some point they reach its equilibrium, right? So sometimes the gas will bubble out, go above the liquid, and then it can bounce around up in the gas phase before it bounces and collides with the surface and goes into the liquid and dissolves. There's some math if you like. If you want to know exactly how many molecules of carbon dioxide have dissolved, that's called concentration. In our next video, we'll talk about different ways of measuring concentration. That's some form of solute amount. So we can talk about how many grams of the solute, how many moles of the solute, what volume of solute. Remember, the solute is being dissolved divided by the amount of the solution. That's the concentration. Again, next video we'll go into concentration a little more in depth. But essentially, we're trying to make the soda pop as fizzy as we can, I guess. Try and get as much carbon dioxide dissolved in there, a lot of solute dissolved per unit of solution. And so the more pressure, that's P here, P stands for pressure. As you increase P, that's going to increase C. More pressure, more concentration. If you lower the pressure, concentration goes down. What's K? K is just a conversion factor. It's Henry's constant. I don't know his first name. Last name was Henry. Professor Henry. He did the research and developed this equation. It's a conversion factor so that pressure might have units of atmospheres, whereas concentration won't. It'll have different units. So you have to convert the units. And so there's a conversion factor to help you do that. Oh, the big concept here, right? Increase the pressure, more gas dissolves. Decrease the pressure, the gas will bubble out, and less gas will be dissolved in the liquid. Okay, that's so important for life and just in everyday situations, right? So how come soda goes flat after you pour it? Well, in the can, it's under pressure, right? So as long as it's sealed and doesn't leak, at the bottling company, they put the soda pop in here and they force carbon dioxide into the top of the can, pressurized it and sealed it. And so as long as you don't open this up, the pressure will be very high inside and the pressure keeps pushing the carbon dioxide gas into the soda pop solution, keeps it dissolved. But the moment you open it up and pour it, well, now there's not much pressure, just 1 atmosphere, normal air pressure pushing on the liquid. It's not really pushing as much as a sealed can was. So now the carbon dioxide can escape. There's less pressure, not much force making it go in there. Carbon dioxide happens to be a non-polar molecule, but water's polar and like dissolves like. Carbon dioxide and water are not very miscible in each other. So the carbon dioxide wants to come out. And with the lower pressure, that's what it does. Eventually, your open can of soda pop will go flat as the carbon dioxide bubbles out and escapes. The concentration of carbon dioxide decreases. It's also important for life. Henry's law. Thank you. Take a deep breath. What's happening there? Well, there's a little diagram from biology, a little interdisciplinary science now. Take a deep breath and the air goes down your mouth, throat, and then down into the lungs, eventually into the little air sacs called, what is that, alveolus? The little air sacs down here is what we're zooming in here. The alveoli, I think is plural, alveolus. So the air from your breath of air goes in here. And what is PO2? Well, the previous video, we talked about Dalton's law. This is partial pressure. So air contains oxygen, carbon dioxide, nitrogen, a bunch of other gases. But if we just consider each gas independently and ask, well, how much pressure does the oxygen of air create? Well, by the time it gets down to lungs, it's 100, I think the units are torr here. 100 torr partial pressure oxygen. The carbon dioxide is 40 torr. So in the air sac, where there's air, the amount of oxygen corresponds to 100 torr of pressure. Carbon dioxide is 40 torr. You remember from Dalton's law that each gas can be thought up as different from each other, and you can actually use PV equals nRT on each gas. So if we know the partial pressure of oxygen, we'll know the number of moles of oxygen. So that's how I like to think of it. Think of it as you take a deep breath of air, there's 100 torr of oxygen, 40 torr of carbon dioxide. Which gas is there a greater amount of? The 100, right? There's more oxygen in the air sac than carbon dioxide. What about in the bloodstream? Well, the blood that's reaching the lung has been deprived of oxygen. The rest of the body has taken the oxygen out, and through metabolism, broken down glucose, blood sugar, with the oxygen and created carbon dioxide and water. So now the bloodstream has a lot of carbon dioxide and not much oxygen. So as the bloodstream approaches the air sac, what's the pressure differential here for oxygen? Well, if you can read it, it's kind of small print. The oxygen here in the bloodstream corresponds to a partial pressure of 40 torr. And in the air sac, it's 100 torr. So where is the oxygen pressure higher? In the air sac. So now let Henry's law take over. The oxygen in the air is higher than the corresponding amount of oxygen in the bloodstream. So the oxygen gets pushed through Henry's law. Excess pressure pushes the oxygen into the bloodstream, helps it to dissolve. The opposite trend is happening with carbon dioxide. Pressure of carbon dioxide, if you can read that number, is 45 torr. In the air sac, it's 40. So now the bloodstream actually has a higher pressure of carbon dioxide. And so now it can bubble out, right? So Henry's law says how much pressure the air over the liquid can push it in. Well, now there's too much carbon dioxide dissolved and not enough in the air sac, which is good for us because the carbon dioxide will then bubble out, fizz out of the bloodstream and into the air sac. And you exhale and you release that carbon dioxide in the air. Take in a new breath. And now the new air components have 100 torr of oxygen, 40 torr carbon dioxide. When you get to the tissues, so you get the oxygen-rich blood. The oxygen-rich blood has lower amounts of carbon dioxide, reaches the tissues down the second part of the slide. Well, then Henry's law is still being obeyed here. At the tissue, there's not much air here, but there's not much oxygen there either. So the oxygen now is at 95 at this point. It can bubble out. It can escape the bloodstream and go into the tissues. Good, because that's what's needed. The tissues need oxygen. And then as they convert the oxygen with sugar into carbon dioxide, well, now the concentration of carbon dioxide in the tissue is higher than the bloodstream. So Henry's law pushes the carbon dioxide into the bloodstream. Nice. Okay, I think that's all for now. Hope you enjoyed a little bit of biology with chemistry. I will see you in the next video.